All right, welcome to our misconception about how water evaporates without boiling. So, in our experiment, what we should have seen was that as we increase our temperature up to a boiling point, or up to the boiling point, the volumes of water evaporate faster. So if we created a graph, our same volume of water, eventually that same volume is going to take less and less time with an increasing temperature. So let's say this is at 70, 160, and so on. So that's what we should see with our water. And what's going on here is interesting, because we think about when we have a pot of water. We think about a pot of water, and inside our pot we've got boiling water. You see the vapor bubbles evaporating. There's vapor coming out, and you see the steam. Is that visible steam the only type of steam that can come off of your water? Well, we could ask another question. How does liquid water decrease in volume? Okay, so does water just mysteriously disappear from a beaker, or does it just do the puddles just mysteriously disappear on the sidewalk? So if you've got the sidewalk right here and it rains, and then there's a puddle, does that water just mysteriously disappear? Well, no, we know we have a scientific reasoning behind it. And so that's kind of what we want to address and see on the molecular level what is causing this. So let's think about if we have a jar of water or a glass of water, and we zoom in and look at what's happening to our normal glass of water at the surface. So in actuality, we have this boundary layer of water, and then we have the water molecules are all collected in a liquid state. This is the liquid phase. And then we have this, what we call air, and that's actually comprised of nitrogen, oxygen, CO2, and water vapor. Okay, and these gases, obviously they're in their gas phase, but if we look at this water vapor, you notice that water vapor is the same molecule as water liquid, but it's in a different phase. And you can have this in the same room as an open container of water, and all that open container is going to be there for a little while. So what's happening? Why does the water not all escape into the air? Well, some of it actually is escaping into the air, but some of it is returning to the water surface. And so when you see that there's a glass of water or something that's staying at a solid or at a liquid phase, if you see the way that I'm drawing my arrows, that means if that water is level, if that water level is not decreasing, that means that you're in a net zero change. Okay, so if you can see these arrows the way I draw them, some of these water molecules are going to be condensing. So let's say this 1, 2, 3, 4, 5 water molecules are condensing at the same time that 1, 2, 3, 4, let's say 5 water molecules are evaporating. Okay, so you have condensation and evaporation happening at the exact same time. Now let's say that we have another container of water, and we decide to turn it up, not to boiling, but let's say we'll turn it to about a little bit above what we would normally call room temperature. Let's say it's about 100 degrees Fahrenheit. That's like right above body temperature. Okay. So we've got our little drawing down here. We've got our red little hot plate. Okay, so what does it look like now at that surface? Okay, so now at the surface, what we might see in the room is that we see that we've got a net evaporation rate that might be higher. Okay, so maybe we've got 6 atoms, water molecules leaving, and 4 water molecules returning. Okay, that means that the condensation is lower than the evaporation rate. Okay, because we've got 1, 2, 3, 4, 5, 6. We've got 6 molecules evaporating, and we've got 1, 2, 3, 4 molecules condensing. Okay, so then let's talk about boiling. Okay, and this is we know that there's lots of water molecules evaporating from this one. Okay, so now that we're boiling, we've got this really hot plate, and this is going to be at 212 degrees Fahrenheit. Okay, and now we've got the rolling bubbles, right? We've got the bubbles of steam coming off, and we can see and feel, we can feel the heat, but we can also see the steam coming off. So now, if we look at that boundary layer, we're going to see almost all evaporation. Okay, so the rate of evaporation is going to be so much more. So we're going to have like 1 molecule in condensation right here, and then all these evaporation molecules. All these molecules are trying to evaporate. Okay, so, and then like 9. Okay, so when we do the math, there's a net difference of greater evaporation. Okay, and so that's why we see when we're at the boiling point, we actually see the evaporating water molecules. And when we're in the middle between room temperature and boiling point, we're at we really don't see how many molecules are leaving, because there's so many returning. And then when we're at room temperature or something else, there's a net zero change, or it's nearly the same amount as many molecules evaporating as condensing. So now when we look at these three different temperatures, so at boiling 100 degrees Fahrenheit, and this is room temperature, this might be like 68 degrees Fahrenheit, or about 70. So when we see this, there's a decrease in the amount of time, because there's a decrease in the amount of time it takes for that water to become vapor, because there's a decrease in there's an increase in evaporation. But we see that with the room temperature, we see that there's still condensation and evaporation. Evaporation is happening and condensation is happening. But when we look at higher temperatures, we see that there's more evaporation happening at those than the condensation, and so we see that there's a net change. And so when we get to boiling, there's so much evaporation happening that those molecules don't stay at that state. They don't stay in the liquid state anymore. And so that's how we can relate it to that temperature versus time graph for like our 5 milliliter sample.